Welcome to this week's first lecture in EE404. In the last lecture, we have seen the concept of linearization for an autonomous system. Remember, in that case, we have chosen the equilibrium point as the operating point for which we apply the linearization. We're going to do a similar thing for time-invariant nonlinear systems. Remember, in a time-invariant nonlinear systems, if it is not autonomous, then we are going to have an input term. In that case, we are going to choose an constant equilibrium input, and then we can apply linearization to such systems as well. So let us start with the linearization of time-invariant systems. In this case, our system, of course, if the system is an autonomous system, is a time-invariant system. So in this case, we are not considering such systems, and that means that linearization of time-invariant and non-autonomous systems. So we are thinking that there is an input term in the nonlinear system. So we have x dot is equal to f of xu, and y is equal to h of xu. This is our system equations. And we would like to convert this system into a linear system form. What is the linear system form for a time-invariant system? So we want the new system in the form ax plus bu and y is equal to cx plus du. In general, this is not going to be possible, so we will not be able to convert this system into this form, but instead we would need to define some new state variable and some new state output and some new input term. Okay? If we define those terms, we are going to see that we can convert such a system into a form given like this, but with different state output and input definitions. We would need those new definitions. So here the first thing that I'm going to choose is an equilibrium point of such a system. We have seen that we can find equilibrium points of time-invariant systems by first converting this system into the autonomous system form and then applying the equilibrium point theory for autonomous systems. So the first thing is going to choose xe and ue such that f of xe and ue is equal to 0. Okay? This means that xe is an equilibrium point for the constant input u of t equals to ue. Okay? So now by having this equilibrium point, we can apply a theory of linearization. So what do we have to do? I'm going to actually linearize. I am going to write a first order Taylor series approximation for this function f around the equilibrium state xe and around the equilibrium input ue. This is really not very difficult. So what I'm going to do is to write f of xu approximately as the zeroth order term of the Taylor series approximation is going to be xe ue plus I will first take the derivative with respect to x, and that is going to be the Jacobian matrix of f with respect to x, and I will evaluate this thing at the equilibrium state and the equilibrium input. The function f is both dependent on x and u. As a result, when I take its derivative, when I calculate its Jacobian with respect to x, the result might still depend on both x and u. As a result, in order to fix those x and u values, I evaluate the Jacobian at the equilibrium state and equilibrium input. Okay? And this is going to be multiplied by x minus xe plus, then I will add the Jacobian with respect to the input, del f over del u, evaluate the result at the equilibrium quantities, and I will write u minus ue. Okay? So now let us give, I really do not want to write these matrices over and over in my equation, so I would like to define them suitably because they are constant matrices. So the constant matrix F is going to be called del F over del X, X equals to XE, U equals to UE, and I will define the constant matrix G as the Jacobian of F with respect to U evaluated at XC and UE. Okay? Now I can write this, I can now write this equality or this approximation as F of XU is, we know that this thing is equal to 0 because we have chosen XC and UE such that they constitute an equilibrium point for the time invariant system. That means that that term is 0. So F of XU is approximately given to us as F times X minus XE plus G times U minus UE. Okay? So now we are ready to apply this approximation onto our system. Let's write it. X dot is F X minus XE plus G U minus UE. We see here that this type of system definition really does not look like this. So here we see that in this linear time invariant system I have this A times X plus B times U. So jointly, if I think that XU is a vector, this is a function like this. X dot is equal to, I have A here, B here. This is an augmented matrix times X times U. Okay? So we see that the right-hand side is a joint linear function of these two variables. But you see that here I have other terms. So F times XE and G times UE are terms which makes this equation not the same as such a one. Okay? So here what I have to do is to define a new state variable and a new input variable to actually make this equation come into the form given like this. Okay? So if I'm here defining my new state vector, the new state vector is going to be called Z, and it's going to be X minus XE. Okay? And I'm defining we know that now that I have repeated several times that this type of state vector change amounts to the change of the origin. So the origin in the Z space becomes XC, the equilibrium point in the X space. Okay? So the origins of Z space and X space are changed. So the reason for such a definition is to pull the origin of the Z space into the equilibrium point. And the new input, I'm going to call this as the input V, and I'm changing the origin there as well. So in the input space, I pull my origin from the 0 vector into this U equilibrium. Okay? So if the input V is equal to 1, that is, if it is a scalar, then that is going to be the distance of U from the equilibrium input. Okay? If the equilibrium input is 2 and if V is 1, that means that U is going to be equal to 3. Okay? Because this tells me that the origin in the V space is the equilibrium input in the U space. If the equilibrium input is U and the distance of V from the U equilibrium is 1, then U has to be 3. Okay? So we have defined our new inputs and new state vector, and now I can actually write this equation with these new variables. So I'm going to write Z dot is equal to, I know that when I take the time derivative of the right hand side here, it's going to be X dot minus 0 because XC is fixed with respect to time. All right. As a result, Z dot is going to be X dot. That means that it is going to be equal to the right hand side here. It is going to be F times X minus XC is Z plus g times u minus ue is v. Okay? So this is our linearized state equation. And you see that it is exactly in the form given like this, except for that we use new state and input variables. So now we are finished with the state equation, and now let us go into the output equation. In the output equation, I have these terms, and I have to convert this equation into a form given like this. So we see that we are not going to be able to do this exactly, but we are going to be able to achieve an equation of this form by, again, redefining the output state and the input. The new state and the input definitions would be the same. I will just change the new output into a new variable by redefining the origin of the output space. Okay? So now let us try to write our approximation for the output function, hxu. In this case, I am going to do exactly the same thing. So I have h of xe, ue, plus, this is a constant term with respect to x and u. And then I have the other terms, del h over del x, evaluated at these equilibrium quantities, times x minus xe, plus del h over del u, x equals to xe, u equals to ue, times u minus ue. Okay? Now I will define my new Jacobian matrices as this. H is going to be defined as the first one, the coefficient of x minus xe. And the second matrix, I will define it as L. That is going to give me the following equation. H of xu is h of xe ue plus h times x minus xe plus L times u minus ue. Okay? Now I can substitute it into my output equation, which is going to give me, this is an approximation here, of course, y of, not an argument here, y is h of xe ue plus the other terms. Now I will take this constant term to the other side and I will define my new output variable. So rho is going to be my new output. It is y minus h of xe ue. So I just changed the origin of the output space to h of xe ue. Okay? And that is going to give me the new equation. Rho is equal to h times x minus xe is my new state, z, plus L, u minus ue is my new input, which is v. Okay? That completes our linearization procedure. All right? So I have the linearized state equation and the linearized output equation. And when I combine these two equations, I get my linearized time invariant system corresponding to this nonlinear system around the equilibrium input and equilibrium states xc and ue. Okay? So now let us quickly solve an example on this. In the example, I will only obtain the linearization of a state equation, which is going to be based on the Volterra predator-prey system. Let us say example. In this case, the equations are given to us as follows. x1 dot is equal to x1 minus u x1 x2, and x2 dot is equal to minus x2 plus u x1 x2. Okay? So you see that this is a variation of Volterra's predator-prey system. I have just selected some constants, 1, -1 here, and these constants, and I have changed these constants, which determine the amount of interaction between two species as U and U, okay? So the input, as you see, enters into the equations in a nonlinear way. Input multiplies the states here. All right. Due to the multiplication of the states here, the system equations were already nonlinear. Now, in addition to this, input also enters into the system in a nonlinear way. So remember these coefficients here, they were B1 and B2. They were actually adjusting the amount of interaction between these predator and prey species. Okay. So here we see that by adding an input here, U, we can adjust from outside this amount of interaction between these two species. All right? And we would like to obtain the linearized version of the system around an equilibrium input and an equilibrium state. So here the first thing that I'm going to do is to take x1 parentheses here. It's going to make things easier for later. So I have 1 minus ux2 here, and I can take x2 parentheses here, and that is going to be -1 plus ux1. All right. So now I can equate both of them to 0. The first thing that I'm going to do is to choose an equilibrium input. Suppose that U of t is equal to, it is this U. Here I don't show the time dependence of the variables, but you should always assume here that U, x2, x1, they are all dependent on time. So U of t, I will choose this as a constant for all time instants. And then I can try to find the equilibrium points of this system corresponding to this constant input. So what I'm going to do here is to substitute U equals to UE. So I will have two equations, x1, 1 minus UE, x2 equals to 0 in the first equation. And this gives me two solutions. x1 is equal to 0 or x2 is equal to 1 over UE. Okay? Now I can substitute this in the second equation to obtain my equilibrium points. If x1 is equal to 0, second equation becomes minus x2 equals to 0. Then this tells me that x2 is equal to 0. So the equilibrium point corresponding to this one, this condition, is xe1 is 0, 0. Let us look at the other one. So I have, if I substitute x2 equals to 1 over UE here, then it's going to be 1 over UE minus 1 plus, remember we were substituting already U equals to UE, so I have UE x1 is equal to 0. This term cannot be equal to 0, that means that the other term should be 0. And that gives us x1 is equal to 1 over UE. Okay? So this means that the second equilibrium point is 1 over UE and 1 over UE. So they are both coordinates are equal, and the second one is the origin. So you see that when I change the input, I can play with the position of the second equilibrium here, but the first equilibrium point never changes. It is independent of the input. So whatever I choose the equilibrium input, the first equilibrium point remains the same, and the second equilibrium point, its position can actually change. So in the state space, we are going to call this state space as the phase plane. The equilibrium points are here, and I would have 1 over UE and 1 over UE here. The second equilibrium point here, xe1, and I have xe2. So you see that if I increase the equilibrium input, then this this equilibrium point is going to be pulled towards the origin. If I decrease the equilibrium input, the equilibrium is going to travel on the y equals to x line towards infinity. So here I see that playing with the amount of interaction between these two species changes the equilibrium position of the system. That is a way actually to control such a system. By playing with the input u, by playing with the amount of interaction, how we are going to play in the actual environmental system, we don't say anything, but if we can play with the amount of interaction between the species, then we can play with the equilibrium point position of this system. So here the task is going to be find the linearized system dynamics, find the linearized system around xe2 is equal to 1 over ue, 1 over ue, and ue. So we are given our equilibrium input and equilibrium state. So I'm only going to apply linearization around the second equilibrium point. It's the more interesting equilibrium point. Remember, the first equilibrium point at the origin corresponds to total extinction for both species here. So the second equilibrium point is much more interesting. So I'm going to linearize the system around the second equilibrium point. Just try to do it yourself for the first equilibrium point. So the first thing that I'm going to do is to actually calculate these Jacobians. Del f over del x, which we called as the constant matrix f, and I will evaluate this at around xe, xe2, x equals to xe2, and u equals to ue. Okay? So if I calculate this Jacobian, remember x has two elements and f has two elements. This is f1, this is f2. That means that this Jacobian matrix, actually the Jacobian matrix of f with respect to x is always a square matrix, okay? Because x has two elements and f has as many elements as x. That means that this is always going to be a square matrix. So this is going to be a 2 by 2 matrix in this case. And I need to evaluate it at the equilibrium input and the equilibrium state. So the derivative, this is my f1. Take the derivative of f1 with respect to x1. You see that it's going to be 1 minus ux2. And derivative of, let me write the derivative of that thing with respect to x2, it is minus ux1. And derivative of f2, the second function, with respect to x1, it is going to be ux2. And in the notes, this is written wrong, so please correct this. This is not ux1. In the notes, this is wrong, so it has to be ux2 as you see. And take the derivative with respect to x2. It's going to be minus 1 plus ux1. Okay? And I will evaluate this matrix at x equals to xe2 and u is equal to ue. Okay? So now let us try to substitute these numbers here. So you see that x2 is 1 over ue, and u is ue. So when I multiply these two, it's going to give me 1 minus 1, that is 0. Okay? Minus ue times 1 over ue, it is going to be minus 1. And ue times 1 over ue, it is going to be 1. And this is going to be 1 over ue 1 plus minus 1, 0. So you see that this F matrix really did not depend on the equilibrium input at all. But in general, of course, you can get equilibrium input dependence there. So let us calculate the matrix G. Del F over del U, in this case, evaluate at the same points. And we see here that F has two components, and the input is just a scalar. That means that in general, Jacobian matrix has as many rows as the function F, and it has as many columns as the variable U. Okay? So here, the number of rows were 2 because F had 2 components. And we had 2 columns because X had 2 components. Here, this is going to have 2 rows and 1 column because U is a scalar. It has only 1 component. So that is going to be a vertical vector here. The derivative of F1 with respect to U is minus x1, x2. Derivative of F2 with respect to U is x1, x2. Then I need to evaluate this at x equals to xe2 and U is equal to UE. Okay? We see that that Jacobian does not depend on U, so I don't care about what U is, but x1 and x2 are important here. I'm going to multiply these two elements, and that is going to be minus 1 over UE square and minus 1 over UE square. Sorry, this is plus. Plus 1 over UE square. So that is my other Jacobian, and I define my new state vector x minus xe2, and that is going to be x1 minus 1 over UE, x2 minus 1 over UE. Okay? So we see that we put the origin of the Z space here, and we do no other change. So my new state coordinates, Z1 is going to be here, and Z2 is going to be here. Okay? And the origin of the Z space is going to be xe2. The new input is going to be defined as follows. V equals to U minus UE, and this I cannot make any modification on this. So we choose the origin of the new input space V as the equilibrium input here. Now let us actually substitute our system write our equations. Z dot is equal to F times Z plus G times V. And in this case, the right hand side looks like this. 0 minus 1, 1, 0 Z plus, that is Z dot, plus I would have here minus 1 over UE square and 1 over UE square times the input V. This is the linearized system dynamics around the equilibrium input and the equilibrium state. And you see that in this question we are only given the state dynamics. That is why we didn't do anything about the output equation. If we had an output equation in the question, then we would try to linearize that one as well. But you know that it is more or less straightforward. So this completes the topic of linearization, and now we are going to go into a new topic that is called phase plane analysis. So the relationship between the nonlinear systems and physics would bring some terminology into nonlinear control systems. It is the case here in the case of phase plane analysis. If this topic was first investigated by electrical engineers, then we would call this topic as state space analysis. Okay? But since the physics people working on nonlinear control define the name of this topic as phase plane analysis, we're going to continue with this terminology. So phase plane is the name given to state space in physics. All right? So that is why we're going to call the next topic in this course as phase plane analysis. And it is in general much easier to work with small dimensional systems. Remember in the course EE404, in order to be able to investigate the performance characteristics of control systems, you have investigated the second order systems, second order linear systems. This is the same in nonlinear control. That is why usually people would investigate or would make phase plane analysis for nonlinear second order systems. That is what we are going to do here. So if you have usually a third order system, fourth order nonlinear system, then you would have to make phase plane analysis using a computer. But the second order systems are easier to work with analytically, and they would really give lots of insight about the higher order nonlinear systems as well. That is why we are going to constrain ourselves to only second order systems while we are making phase plane analysis. So let us start with our new topic. Let me get rid of this part as well. Our new topic is second order systems and phase plane analysis. What we would like to do in this part is really not difficult to understand. We're going to have a second order system, nonlinear system in general, and this system would look like this. Of course, we are considering the autonomous system, because if you don't have an autonomous system, then we know that we would have to deal with the input as well, and the input is going to change the system dynamics. So what we would like to do in this part is to draw the trajectories of a nonlinear system onto the state space, x1 and x2. If I have an additional variable, then depending on the input u, this dynamics or these trajectories would change. So we know that when we have an input, then we can set that input to a constant, and we can get an autonomous system. So if you would like to draw the trajectories of a time invariant second order nonlinear system like this, which also contains an input term, then we can do it by first converting that system into an autonomous system by selecting the input or setting the input to a constant. Okay? So I have here an autonomous second order system. So if this system contains an input, then you have to set it to a constant, and you would get the autonomous version of that system, and then you can make the same analysis on that system. If you want to investigate the different effects of the effects of different inputs, then you change the constant input to another value and draw the trajectory once more. So we are interested in the trajectories of the system in the state space. As I told you, the state space in physics is called phase plane. Okay? Then that means that we would like to draw the trajectories of this system in the phase space, and the analysis that we would be making in that case is called phase plane analysis. Okay? So here I have my phase plane, x1, x2, and we can start the trajectory anywhere we like. This is my x0. Of course, I'm defining my state vector as x1 and x2. So this is my initial x1, and this is my initial x2. And then depending on the functions f1 and f2, I would have a velocity vector. Remember that it is shown as f of x. So if I show this system in the following form, x dot is nothing but f of x, and f of x is nothing but f1 of x and f2 of x. Okay? Here are these functions f1 and f2. So given the initial condition, I will start somewhere here, let us say, and then I will substitute the initial condition into my functions f1 and f2, and I will get the velocity vector. And then I know that this trajectory is going to go in this direction, in this velocity vector direction. And when I come to this point, it is going to be a different point than my initial condition. I will substitute it again into the f function, and that is going to give me another velocity vector, and I will move in that direction to obtain the new point. So we can continue in this manner to draw the whole trajectory of the nonlinear system. So this is not really the way to draw the trajectories of such a system. By phase plane analysis, we would be going after some much more strategically involved method here. Okay, this is how a computer would draw this trajectory. It would start with an initial condition, and it would calculate a vector, velocity vector. Then it would move in that direction infinitesimally, and then it would calculate another velocity vector, and it would move infinitesimally in that direction, and it would draw a trajectory like this. This is what a computer does. So by seeing all of the functions at the same time, we want a much more sophisticated method to make an analytical analysis of these trajectories. All right? And that is going to be called phase plane analysis. And we are going to see that that type of analysis has also a disadvantage. So a computer can draw a trajectory of a nonlinear system for an arbitrary f1 and f2. But we here want to make a mathematical analysis or an analytical derivation of these trajectories. That means that we are going to be constrained to only very, very simple functions f1 and f2. Okay? So phase plane analysis is good. It gives us the analytical way to work with these trajectories, but we're going to see that it's going to be really simple nonlinear systems that we can deal with phase plane analysis. If the functions f1 and f2 are too complicated, then we would have to resort to the use of a computer at the end to obtain complicated trajectories. All right? So this thing that I have drawn here is a phase plane trajectory. Phase plane trajectory. Okay? So you see that it is composed of a curve plus a direction. Okay? So direction is also important for us. In which direction is the trajectory going to move? That is also important for us. So here, the first thing that I would like to do is to draw the phase plane trajectory of a very, very simple linear system. And then that is going to illustrate us what the difficulties of phase plane analysis, or how we can actually approach this problem. For that, I'm going to consider the following example. It is going to be a very, very simple system. So I would have the harmonic oscillator given like this. A mass whose mass value is 1 kilogram, let us say, and a spring with a spring constant 1. And let me say that the displacement variable from the equilibrium is here called y. I'm calling it y because I'm going to define a state variable with the notation x here. So I don't want the displacement to be confused with my state vector. So that is why I define the displacement variable as y here. Now, in order to be able to apply phase plane analysis or state space analysis, I need a state for this system. Currently, I don't have any state. I have the output, which is this displacement, but still nothing called state here. So that is why I am first going to obtain the differential equation representation of this system, and then we'll define my state vector, and then I will come to a point where I can apply state space analysis or phase plane analysis of the trajectories. So here I have, let us obtain the mathematical model. Mass times acceleration is going to be equal to the net force applied onto the system. So you see that there is no external force here, but there is only spring here, and the friction force is zero, because the friction coefficient is zero here. So I have the only force applied here is going to be minus ky. Remember here, if y is positive, the spring is going to pull the mass to the other direction, and here I need to count on the right hand side the net force in the direction of increasing y. We see that if y is positive, the force applied by the spring onto the mass in the direction of increasing y would be negative force, okay? Because it would be pulling the mass in the other direction. That is the force to decrease y. That means that I need to put here a minus sign. So here and I would in general also have b times y dot, but here b is equal to 0. That is the friction force, so I can remove this term from here from the start. And we know that such a system would oscillate forever. If we give to this system a non-zero initial condition, we know that it is going to oscillate forever. Why? Because it can never dissipate the energy, that is initial energy that is given to it, because the friction is zero. Friction here is the energy dissipation method here. So if the system cannot dissipate the energy, then it's going to move forever. So now I can substitute m equals to 1, k equals to 1. That is going to give me the system y double dot is equal to minus y. Okay? So you see how this is a second order linear differential equation. Now I can define my state variables. So let us define our state vector x as y and y dot. And then let us try to find my state equation. X dot is equal to, so I have here my state. X dot, the variable, the derivative of the first variable is going to be y dot. Y dot is just the second state variable. That means that I would have 0, 1 here. And the derivative of the second state variable is y double dot. And we see from the equation, system equation, that y dot double dot is equal to minus y. That means that I would have minus 1, 0 here. So this is my state equation. Now what I'm going to do is, here we didn't see yet the phase plane analysis tools that we are going to employ for such a linear system. We are going to see in the next lecture that the way to employ a state space analysis to such a linear system would be to find the eigenvalues and eigenvectors of this matrix. But currently I don't have such tools. I'm assuming that I haven't started with phase plane analysis tools yet. So currently I will try to obtain the phase plane trajectories of such a linear system by looking at the solution of this differential equation for an initial condition. So suppose that my initial state x0 is given as y0 and 0. So the initial speed is 0 and initial position is y0. So I take the mass from the equilibrium and I would put it here at the point y0 with 0 velocity, and I would leave it to itself, and it's going to oscillate, and I would like to draw the trajectories in the phase plane for this system. So since I don't want to calculate eigenvalues and the eigenvectors here, what I'm going to do is to try to solve this differential equation. This is not going to be really a phase plane analysis method here. Solving a differential equation, or in general, solving a differential equation in this nonlinear form would be very, very difficult, and analytically it would be very, very difficult, and it would be impossible sometimes. So that is why this is the solution method that I apply here is not going to be a phase plane analysis method. So what we would like to do in phase plane analysis would be try to draw these trajectories as closely to the reality as possible without actually solving these differential equations. Okay? That is going to be one constraint of phase plane analysis. So we will never obtain the solution of these differential equations. We will try to draw the trajectories without actually solving these equations. So the method that I apply here is not a phase plane analysis method that we're going to see. So now let us go into the Laplace domain with this differential equation, and let us try to solve it for this initial condition. So when I go into the Laplace domain, I would have S times. Before I continue with the Laplace domain, I will ask you this. Maybe you, of course, you know this. If I try to calculate the Laplace transform of f dot of t, if I want to calculate this, then what can you say about this quantity in terms of the Laplace transform of f? This is equal to S times Laplace transform of f of t minus f of 0. The initial condition. Okay? So I'm just going to apply that rule here. So the Laplace transform of x dot is S times x of s. So this is nothing but f of s here. So this is s times x of s minus the initial condition is going to be equal to Laplace transform would commute with linear transformations like this. So I will call this matrix as A. And that is going to be A times x of s. Okay? I will take this ax to the other side. So I would have s identity minus A. Capital X of s is equal to x0. We know that I can actually take this si minus A to the other side by inverting it. So x of s is Si minus A inverse times the initial condition vector x0 here. Okay? Let us calculate Si minus A here. Si minus A is S minus 1, 1, and I would have S. Then we know that I need to invert this. Si minus A inverse is going to be 1 over the determinant. I would have a matrix here, the adjugate matrix, and 1 over the determinant here. Determinant is s squared plus 1, and the matrix here s 1 and minus 1. All right? So now I can multiply this Si minus A inverse with the initial condition. That is my initial condition. Multiply this matrix with y0 and 0 vector. So when I multiply it, I know that the first column is going to be multiplied with y0. Okay? So I have x of s is equal to this times that initial condition. Y0 is going to multiply everything, and I would have the first column. I have the determinant, and I would have the first column here, s minus 1. Okay? If I actually construct this vector, if I write this in terms of its elements, I would have s over s squared plus 1 times y0. I can write the y0 to the other side. And I would have minus 1 over s squared plus 1 y0 here. Okay? So now you see that I know the Laplace transform of x1 and x2. Laplace transform of x1 of s, I show it with capital X1 of S, is I have here S over S squared plus 1 times Y0, and Laplace transform of X2 of S is minus 1 over S squared plus 1 Y0. Now you would have to remember some Laplace transform knowledge here before we can continue. Now I would like to calculate what x1 of t is and what x2 of t is. Okay? So if you think about Laplace transformation S over S squared plus 1, what would be the inverse Laplace transformation of S over S squared plus 1? If you look at the roots of the denominator, you see that S squared plus 1 is equal to 0 at S equals to plus minus j. So I have complex roots, so that means that I will have sine t or cosine t, some oscillatory terms. Is this sine or cosine? The way I remember this is as follows. So I have cosine omega t in Laplace domain and sine omega t in Laplace domain. Both of them has the same factors in the denominator. Okay? And one of them has s in the numerator and the other one has omega in the denominator, in the numerator. Okay? Which one has omega and which one has s? So the way I usually remember this is that if I substitute minus omega instead of omega in cosine, what is cosine omega t? What is cosine minus omega t? I know that cosine is an even function, so cosine minus omega t has to be just cosine omega t. That means that if I substitute in the Laplace domain minus omega instead of omega, this Laplace transform should not change, because substitution of minus omega into omega does not change cosine. Okay? That means that in its Laplace transform, when I substitute minus omega instead of omega, this Laplace transform should not change. On the other hand, if I look at sine, if I substitute minus omega instead of omega here, the sine would be negative sine. Sine minus omega t is minus sine omega t. Okay? That means that if I substitute minus omega into omega here in the Laplace transform, I need to obtain the negative of the Laplace transformation. So which one has s, which one has omega? Which one has s? So we see that this one is s and this one is omega. Okay? So here I have this one, which is going to give me y0, and this is cosine t, and this one is going to be minus y0, and I would have, you see, sine of t. All right? So I solved the differential equation. It was a very, very simple A matrix, and I could solve the differential equations in this case, all right, to obtain the phase plane trajectory. In general, this is not going to be possible for nonlinear systems. That is why we have to find other methods to be able to draw the phase plane trajectories of the system. So here I have x1 of t, x2 of t, and what I have to do is to draw these x1 of t and x2 of t into x1, x2 plane. In the phase plane, we need to get rid of the time variable here. Okay? So in the phase plane, when I draw a trajectory, I lose the time information. Okay? So if I draw here a trajectory, then it would be an equation of the following form. Let us say y1 is equal to, I can have here a function, let us say s of y2. The trajectory of this form, I will obtain an equation like this. y1 is equal to a function of y2. In this equation, there will no longer remain a time variable, or I would obtain the reverse. This is s1, s2 of y1. Or sometimes I won't be able to obtain any of these forms. Sometimes I will just obtain s3, y1, y2 is equal to 0. An equation of this form that would connect, by the way, what I mean here, these x1 and x2s, not y's, okay? Sorry for this. In general, a phase plane trajectory would be looking like these equations. x1 is a function of x2, or x2 is a function of x1, or x1, x2, and their functions are taken and the result is 0. So a phase plane trajectory will not contain the time variable in general. That is why when we have the solution of the differential equation given like this, I need to get rid of the time variables. I need to actually get rid of time t from those equations to obtain my phase plane trajectories. So how can I get rid of these time variables from these x1 and x2? So you see that both of them depend on time. So what I can do here is to express t as a function of x1 from the first equation. Just divide x1 with y0 and take arc cosine and write what t is in terms of x1 and then substitute it here into the second equation. Then you would get x2 is equal to some function of x1. You would get this form. But here, that is a general way. Here, there is an easier way. We know that cosine square plus sine square is equal to 1. So if I take the square of both sides and when I sum them, I would get rid of time automatically. Okay? So here, if I sum x1 square plus x2 square, that is going to be y0 square cosine square plus y0 square sine square. If I take y0 square parentheses, then you see that in the parentheses I would have cosine square plus sine square, which is always 1, whatever t is. All right? So this is my phase plane trajectory in this case. All right? And you see that this is the equation of a circle in x1, x2 plane. That means that my phase plane trajectories would be looking like circles in phase plane, depending on their initial condition. So this is y0 point is here, and the phase plane trajectories would be circles. So here I will ask the question, okay, I now know what phase plane trajectories would look like for different initial conditions. How can I find the direction on these trajectories? Well, the phase plane trajectories are nothing but circles here. And you see that this is an oscillatory motion because of the harmonic oscillator that we have here, a very basic oscillating system. So how do I find the direction? Whether the rotation is going to be clockwise or counterclockwise in the phase plane. So we see, so just choose a point on this trajectory. I'm choosing the initial point here, but you can select any point on any one of the trajectories. And I want to know what the velocity vector would be at this initial point. What is that initial point? It is x0, which is equal to y0, 0. I'm wondering here, what is x dot of 0? Okay? The velocity, the initial velocity of the trajectory. Initial velocity of the system state. So what is this? This is f of x0. All right? Remember, our differential equation is x dot is equal to f of x. That means that x dot of 0 is f of x0. But here f of x0 is nothing but a times x. A times x0. So multiply this matrix with x0, then you are going to find the initial velocity vector. Okay? Multiply this matrix with x0, you will find the initial velocity vector. But this is nothing but y0 times the first column, 0 minus y0. Okay? I here assume that y0 is positive, okay? That means that my initial velocity, initial x velocity will be 0, and initial x1 velocity will be 0. x1 will not change, but the initial velocity for x2 is minus y0. So do you think at this initial point the trajectory is going to move in this direction or in that direction? That is the question here. The x component of the velocity is 0. The y component is going to be, if y0 is positive, the x2 component is going to be negative. That means that this is going to be my initial velocity. That means that these trajectories are just clockwise trajectories here. Okay? So what happens if I take y0 here? Then y0 becomes negative, and minus y0 would be positive, meaning that I would have a velocity given like this. That really doesn't contradict anything, because this rotation is given like this, and the velocity here is perfectly downwards, and the velocity here is perfectly upwards. Okay? So each one of these trajectories, each one of these circles would be called a phase plane trajectory. Phase plane trajectory. When you draw multiple trajectories like this on the same phase plane, the overall figure, when you draw multiple trajectories on the same phase plane, just like this, this trajectory is not the same as this trajectory, or it is not a continuation of the first trajectory. These are different trajectories of the same system. If I draw multiple such trajectories on the same phase plane, the figure that I draw is called a phase portrait. Okay? That is the name given to drawing multiple trajectories corresponding to different initial conditions on the same figure. Okay? And this was just an introduction to the phase plane analysis. I have shown you what we are going to get at the end, but I have not yet shown you how we're going to work in the phase plane analysis, what type of tools we are going to use. When we have such a system, in this case I have solved those differential equations, but that is not going to be our way of applying phase plane analysis. We're going to see that when I have a linear system like this, and when I want to draw its phase plane trajectories, I will first find the eigenvalues and eigenvectors of this matrix, not try to solve the differential equations. Okay? And we're going to see that the eigenvalues and eigenvectors will be an important part of this course as well. Okay? So the last question here, what is the equilibrium point of this system? The equilibrium point, just look at the determinant of this matrix. We see that the determinant is non-zero. That means that xe equals to 0, 0 is the only equilibrium point of this system. Okay? So this equilibrium point is here. When I leave the system here, it's going to remain there forever. So when I have around the equilibrium point circles, or in general ellipses, some oscillatory motion like this around an equilibrium point, we're going to give that equilibrium point a specific name. I'm going to call that equilibrium point as a center in general. And we're going to see that when we look at linear systems and when we look at their equilibrium points, the motion of the trajectories around equilibrium points will be one of some very specific types of motion. We're going to name each of the equilibrium points based on what type of trajectories that we would observe around that equilibrium points. These types are going to be, for example, nodes, or they would be centers, or they would be focuses, or they would be saddle points, as we would see, depending on the motion of the system around equilibrium points. And the motion around equilibrium points will be determined by the eigenvalues of this A matrix. Then after we see the phase portraits of linear systems, we are going to go into the phase portraits of nonlinear systems, and we are going to see that linearization and the eigenvalues of the linearized system matrix here will have a very important role in us trying to draw the phase plane trajectories of nonlinear systems around their equilibrium points. Okay? I have really talked a lot in this lecture. I have really talked a lot of things that we're going to see in the future. So if you didn't understand any part, like what is a node, what is a focus, or what is a saddle point, then know that we are going to see those in much more detail in the future parts of this course. So it is sufficient that only you understand what I have done so far, and not the things that I have said here only verbally. We are going to see them in more detail. But that's all for this lecture. Thank you very much. Bye.